Right. Yes. Yes, you may. The correlation between the age and height of children under the age of 12 is found to be R equals 0.60. So the only thing R is good for finding on its own is describing the direction and the strength of a correlation. At least that's all that we've talked about in here. So R finds the strength and the direction of the correlation. So using just R, we could say that the relationship between age and height of children under 12 is a moderately strong positive correlation. Is that any of these? No. Okay. R is not telling us how often we accurately predict heights. Got it. That's not what R tells us. R tells us about the strength, but that does not mean that we're going to get an accurate prediction 60% of the time. The height is generally 60% of a child's age. That's also not something that R tells us. For every 1 year older a child is, the regression line predicts an increase of 0.6 foot in height. What they're describing here is the slope. And R and the slope are not the same thing. So I can throw those three out right away. These other two options have 36%. How could you take an R value of 0.60 and end up with something that is 36%? Square it. R squared would be equal to 0.60 squared is equal to 0.36. 36%. R squared is the coefficient of determination. The coefficient of determination tells you that when you are using your least squares regression line to find these predicted amounts, how much of the change or the differences that you see in the output is because of the change that happened in the input. That's what the coefficient of determination tells us. So one way to think about this. Anybody in here have a job? When you work more hours, what happens to your check? It goes up. Does it go up in a predictable way? Yeah. It should go up in a predictable way. It should go up in a predictable way before taxes that is directly related to how many hours you worked. So if we looked at before taxes on your check stubs, you would say that R squared was 100%. 100% of the change or the variation that you see in the dollar amount that you get on your check is because of the differences in input, the differences in hours worked. Thank you. Once you start figuring taxes into it, it gets a little bit more muddy, right? So now we're not looking at 100% of the change in your wages is because of the hours worked, but a large percentage of the change in your pay is because of the hours that you worked. That's what R squared is telling us. So for this one, R squared is 0.36 or 36%. We say 36% of the variation in height is accounted for or is because of the linear model that relates height to age. So this one is C. E is just silly. 36% of the time, the least squares regression line accurately predicts height from age. We're going to be getting close with this regression line equation. We're going to be getting reasonable predictions, but that does not mean that you will accurately predict, get it right on the nose 36% of the time. That's not what R squared is telling us. All right, let's see. Let's look at 2.7 next. I feel like we looked at 2.7 the other day. Yes. Do you want to go grab it? Yeah, we absolutely do that. All right. Looking at 2.7, we talked about this one a little bit yesterday. I don't think we actually popped it into the calculator though. You can do this using inverse norm, or you can do this using table A. You can go look up 0.05 on table A. Sorry, 0.05. You looked it up in the middle of table A, and that would give you a z-score. So if you decide to go that route, looking in the center of the table here for the thing that is the closest to 0.05, looks like the closest I'm able to get, it looks like it's halfway in between negative 1.64 and negative 1.65. So let's split the difference and say z is negative 1.645, halfway in between negative 1.64 and negative 1.65. Then we would be using z equals x minus mu over sigma. So I'd have negative 1.645 is equal to, we don't know what x is, that's the thing that we're trying to find. We do know mu, that's 450, and we know the standard deviation is 20. So then from here, you would multiply both sides by 20. Don't have quite enough room to do this, but then I would add 450 to both sides. And if you grab your calculators and you do 20, clear all that out, 20 times negative 1.645 plus 450, you get 417.1. And so we're going to round that up to the closest whole number, and we get 418. If they have only 418 unbroken briquettes or less, then the bag will be replaced, or they'll reimburse them. Does anybody have one that they want to look at? Because I'm going to wait until Damon gets back to go over any of his. 1.12? Absolutely. 9, 10, 11. 1.12, sorry, I'm in the twos. 1.12. There we go. 1.12, a linear regression was performed using the following 5 data points. A, 222, B, 10.4, C, 6.14, D, 14.2, and E, 18, -4. The residual for which of the 5 points has the largest absolute value? So I would use my graphing calculator. Especially given the fact that this is a multiple choice question. If I was looking at this on the exam, I'd use my graphing calculator to help me with this one because this is going to be your fastest approach. So stat, edit, clear this out. Come on. And then down list 1, I'm going to put the X's. And down list 2, I'm going to put the Y's. So I'm going to put 2, and then 10, 6, 14, and 18. So those are all the X's from the ordered pairs. And then I'm going to come over to list 2 and I'm going to put the y values. 22, 4, 14, 2, and -4. I want to make sure that my scatter plot is turned on so that I can look at this graph. So I'm going to go second and y equals. If you look in blue, it says stat plot up above. That's what I'm accessing. I'm accessing the stat plot menu. I want to make sure that plot 1 is turned on, which it looks like it is, but I want it to be a scatter plot. If you look at that little picture right there, does that look like a scatter plot? No, looks like a histogram. So I'm going to enter this, make sure that it's flashing around on, and it should be completely dark. If it's flashing around off or it's completely dark around off, then the whole thing has been turned off. I'm going to come down to type. This first one here is the scatter plot, so I'm going to hit enter. We're going over 1.12. I want it to be pulling the X's from list 1 and the Y's from list 2. So now I want to go and look at this, and I want to make sure that it zooms in enough that I can actually see these points. So I'm going to hit zoom, and choice number 9, zoom stat. It doesn't always get it perfect, but it at least gets it so I can see it on the screen. So I'm going to go with option number 9 here. And that's what the scatter plot looks like. Now, if you were to draw in what you think looks like the line of best fit, can you guys agree that it would probably look something like that? There-ish. We're looking for the one that has the largest residual. Residuals are the vertical distance of a point away from the line of best fit. Which one of these points looks to have the largest distance between the point and the line of best fit? The third one, this one right here. So now I need to figure out which point that is. And to do that, I'm going to use the arrow keys. As soon as I start hitting the arrow keys, there's this little cursor that shows up on the screen, and I can control that with my arrow keys until I get down to that point. And I'm going to get it as close to right on top of that point as I possibly can. If you look down at the bottom of the screen, it says X is 10 and Y is almost 4. So I'm pretty sure that that dot is the one that's at 10.4. So then I'm point right here. And so I would go with choice B. There is a way where you can make the graphing calculator graph the line of best fit for you. Would you guys like to see that? Okay. All right, so still back here. To make it graph the line of best fit, we need to know what A and B are, the predicted y-intercept and the slope. So you go to stat, you arrow over to calc. We want linear regression, A plus BX, predicted y-intercept plus slope times my x variable. So I'm going to go with option number 8. X list needs to be coming from list 1. Y list needs to come from list 2. I don't want a frequency list at all. We're not talking about probabilities. We just have scatter plot. I'm going to come down to calculate. There's my A and there's my B. So when it even tells me here, I can take this now in this form, substituting in 23.6 for A and negative 1.6 for B. If I hit y equals, not second and y equals, just y equals, that was, sorry, I did not write that down. That was 23.6, I think. Okay. Sorry, I should have written it down. 23.6 and negative 1.6. Y equals 23.6 minus 1.6. And then to put the x for the variable, that's this button right here next to the alpha. It says x, t, theta, and n. It's just got a whole bunch of variables there. Now, if I take and graph this, it puts that line of best fit in there for me. So far, so good? All right. So that's 1.12. let's look at let's look at 2.1 next. 2.1. And then we'll look at 2.4. We talked about 2.1 yesterday. What we're looking at when we want to know the possible length of the right side whisker is, if I'm looking at a box plot, and these whiskers are as long as possible so that this value right back here is not an outlier, but it's almost an outlier. What we're looking for is just how long is this right here. And that maximum length before things start to be outliers is 1.5 times the IQR. And so that's what we did to find 33. We did 1.5 times the IQR. IQR is Q3 minus Q1. So we did 40 minus 18. That gave us 22. 1.5 times 22 gives us 33. So that is choice A. All right. 2.3 and 4. Let's see, 2.3 is kind of taking us to the right side of the page and then the left, but let's go ahead and do that anyway. 2.3. In a certain large population of adults, the distribution of IQ scores is strongly left skewed with a mean of 122 and a standard deviation of 5. Suppose 200 adults are randomly selected from this population for a market research study. For simple random samples of size 200, the distribution of sample mean IQ score is. So we're looking at a sample mean. That's an X bar. So I want to know about the sampling distribution of X bar. This is what we were just talking about in chapter 7. So simple random samples of size 200. 200 is greater than or equal to 30. So my central limit theorem applies here, which means what? Means it's approximately normal. All right, so not left skewed, not exactly anything. So throw out the ones that say exactly. So approximately normal. Both of these have the same mean as the population mean, 122. The population standard deviation is 5. What happens when we increase n? What happens to the standard deviation? It decreases. And the way it decreases, come on, is we have sigma of the population divided by the square root of n. That gives me the standard deviation of the sampling distribution. So I know it's not going to be a standard deviation of 5. I don't even need to plug this into my calculator. I've eliminated all of the other possible choices, so this has to be E. (2.4) A 10-question multiple choice exam offers 5 choices for each question. Jason just guesses the answers, so he has a probability 1/5 of getting any one answer correct. You want to perform a simulation to determine the number of correct answers that Jason gets. What would be a proper way to use a table of random digits to do this? So we didn't talk a whole lot about tables of random digits. It was talked about in your book, but we didn't really talk about it during class. So when we talk about digits, we're talking about a single digit, so 0 through 9. And a table of random digits takes these 10 digits, 0 through 9, and has them in a random order, just repeated randomly over and over and over. This got used a lot before random number generators were easily accessible things. Now we've got Google random number generators and all kinds of different random number generators, and we've got them built into the calculator. So we don't really use tables of random digits very much anymore. This is becoming more of an archaic idea, which is why I didn't really talk about it very much in class. When you're looking at a table of random digits in this situation, I know I've got digits 0 through 9. So that would be 10 digits. Something that would represent a 1/5 chance. So how many of these, and that's 1/5 chance of getting it right. So how many of the digits 0 through 9 should we be looking at if we want to model a 1/5 probability? 2. Pick 2 digits to be correct, or to model what a right answer would be here. Does it matter which 2 digits you choose? Nope. You can choose 0 and 1. You could choose 5 and 6. You can choose 8 and 9. It doesn't really matter. And then how many random digits should we look at if we want to simulate this 10-question quiz? 10. Because each one of these numbers would represent an answer to a question. All right, so let's read through these answer choices. It says 1 digit from the random digit table simulates 1 answer with 5 equaling correct and all other digits equaling incorrect. Would this give a 1/5 probability? No. That would give a 1/10 probability. So we're going to throw this one out. All right, option B, 1 digit from the random digit table simulates 1 answer with 0 or 1 being correct and all other digits incorrect. 10 digits from the table simulate 10 answers. Does that work? Yes. We've got 2 of the numbers, 0 and 1, being correct choices. So that's my 1/5 probability. And we are going to look at 10 digits to simulate 10 answers. This is the correct choice here. What's the problem with C? Yeah, it's got a 50-50 chance of being right instead of a 1/5 chance of being right. What's wrong with D? What'd you say? We don't want to ignore the repeats here. If you're taking a multiple choice test, can you choose C more than one time? Yes, you can. So we don't want to ignore the repeats when we're talking about this particular situation. 2 digits from the random digit table simulate 1 answer. That doesn't even make sense in the context. So that's why those other choices are incorrect. All right, let's look at what else we're going to hit on. We talked about that one. Let's look at 1.6. 1.6. The figure shows a normal density curve. Which of the following gives the best estimate for the mean and standard deviation of this normal distribution? So the mean, I want to go straight down from the bump, which is falling squarely in between 200 and 250. So I know my mean is about 225, so I can throw out options A and B right there. Standard deviation. Do you guys remember our empirical rule? 68, 95, 99.7? So I'm thinking 99.7 right now, because 99.7 is almost the whole thing, right? And that is 3 standard deviations out on either side. So I'm just going to look at one side. So let's say from here to here. If that is 3 standard deviations about, how far is that to go from 225 to 400? $175. So 3 standard deviations is 175 units. And then I'm going to do that 175, divide that by 3, which would give us what? You said 58.333? 3 repeating. So this is about 1 standard deviation. Remember, I was just kind of eyeballing it off the graph too. But I know that from the mean to the end is approximately 3 standard deviations. It goes a little bit beyond 3 standard deviations. But it's about 3 standard deviations. But that does give me enough to narrow this down. I know 25 is way too small. And I know 275 is way too big. So this has to be choice C. What else would you guys like to look at? And if the answer is nothing because our brains are fried after the 5th period final, that's also fine. Yes, Deborah. Okay. Yes. 2.16. And 2.17? 2.10? Okay, so 2.16, then 2.10. There's 2.10. There's 2.16. According to the U.S. Census, when I see census, I know we're talking about the whole population. A census, by definition, is the whole population. It's gathering information from the whole population. According to the U.S. Census, the proportion of adults in a certain county who owned their home was 0.71. And this is a proportion. So this is P, where P means proportion, not probability. We're not. And I know we recycle letters in math. I apologize, guys. I don't get to make those decisions. But capital P with parentheses is probability. Lowercase p is proportions. An SRS of 100 adults, underline that. 100 adults, so I know N is 100. In a certain section of the country found that 65 owned their home. So we're talking 65 out of 100, right? And that came from a sample. That means that's a p hat. If it's 65 out of 100, what is p hat as a decimal? 0.65. Which one of the following represents the approximate probability of obtaining a sample of 100 adults in which 65 or fewer own their home, assuming that this section of the county has the same overall proportion of adults who own their home as does the entire country? So first of all, I'm looking for a probability where we have a P and a P hat. So I'm looking at standardized test statistic, or Z is equal to statistic minus parameter divided by the standard deviation. My statistic is p hat. My parameter is p. And the way we calculate the standard deviation when we have p is we have the square root of p times 1 minus p over n. So immediately I can throw out options A and B. What are A and B looking at here? Yeah, this is like successes and failures, right? This is looking at it as a binomial random variable. This is going to give me the number, not the proportion. I'm going to end up with a probability for a number instead of a probability for a proportion. What was our p hat? 0.65. P is 0.71. Well, so far, all of those have them correctly up here. So our big differences are coming in the denominators. Why is it not D? They used P hat there instead of P. So that's not right. What's wrong with E? Yeah, the square root is only around n. It's not around the whole thing. So the correct answer here is C. All right. Let's look at 2.10. Social scientists are interested in the association between high school graduation rate, HSGR, measured as a percent. Oops. And the percent of U.S. families living in poverty, POV. Data were collected from all 50 states and the District of Columbia, and a regression analysis was conducted. The resulting least squares regression line is given by this right here. So we are predicting families living in poverty based on the high school graduation rate. It says R squared is 0.802. Based on the information, which of the following is the best interpretation for the slope of the least squares regression line? What is the slope? Negative 0.62. There's the slope. I know it's the slope because it's being multiplied to a variable. Anytime I have a linear equation and I have a number being multiplied to a variable, that is the slope. Is that a positive or negative slope? Negative, which means it's going to increase or decrease? Decrease. So for each 1% increase in the graduation rate, so as this goes up 1%, we expect the percent of families living in poverty to decrease by what? 0.62. So which option are we looking at? C. When we're talking about slope, we're always going to have an increase of 1 whatever in our x variable. And then the slope tells me about the resulting output or change in the output for my y variable. What's the problem with E? They switched the x and the y. So we're not looking at an increase here when I'm talking about the slope. I'm looking at an increase here when I'm talking about the slope. An increase of 1 there, and then what happens to our output or to our POV in this case. All right. What else would you guys like to look at? Yes? 1.13 and 2.19. Let's do 2.19 since we're sitting right there, and then I'll go back to 1.13. 2.19. When people order books from a popular online source, they're shipped in boxes. Suppose that the mean weight of the boxes is 1.5 pounds with a standard deviation of 0.3 pounds. The mean weight of the packing material is 0.5 pounds with a standard deviation of 0.1 pound. And the mean weight of the books shipped is 12 pounds with a standard deviation of 3 pounds. Assuming that the weights are independent, what is the standard deviation of the total weight of the boxes that are shipped from this source? So each of these things that they described here is a random variable. The boxes don't all weigh the same. They average 1.5 pounds. They have a standard deviation of 0.3 pounds. So I'm going to use B for the weight of the boxes. Packing material, same thing. It's not a set amount. It's an amount that can fluctuate. That means it's a random variable. So here's the weight of packing material. And then we have books. I'm going to use K for books because I already used B. Weight. Oh, I need to do this in orange because that's what I did up above. Weight of books. We want the standard deviation for the total weight. So we're going to be adding B plus P plus K. But we are interested in the standard deviation of that. So I want the standard deviation of B plus P plus K. Can we just add the standard deviations? No. What can we add? The variances, but then we're going to have to square root it at the end. So I need the standard deviation for the boxes squared plus the standard deviation for the packing material squared plus the standard deviation for the books squared. So I've got the square root of 0.3 squared plus 0.1 squared plus 3 squared. I think, can somebody please double check me on the calculator? I think that ends up being the square root of 9.1. And so when you square root 9.1, you end up getting approximately 3.02. And then you said 1.13. Oh, 2.7. Sorry, 2.7. Yeah, 2.7. I think we talked about this one while you were actually out of the room. I apologize. Okay. 1.13, absolutely. 1.13. So 1.13, here's what I would do. Every single one of these is out of 140 patients. So I'm going to take each of these and I'm going to divide by 140. This will change things into percentages for me. When I do that, this first one comes out to be about 0.04. Second one is about 0.17. Third one is about 0.32. About 0.27. Approximately 0.14. 0.5 or 0.05 and 0.01. The median is what percentile? 50th percentile. So I want to figure out where the median is. I want to figure out where the 50th, like where is 0.50 in here? If I add these two together, I'm just going to look at myself adding from left to right. If I add these two together, I get 0.21. Not big enough. That's not going to contain the median. If I go all the way down to here, though, and include the 0.32, now I'm at 0.53. And notice I had to include almost all of these to get to 0.53. Like 0.50 is going to be really, really close to the end of this list. So I know that my median is going to be close to 30. But not over 30, because 0.53, notice I went up to, but not quite 30, so like 29.99999 minutes. So I can get rid of those three choices right there. Now I'm just looking for a reasonable IQR. How do you calculate IQR again? IQR is Q3 minus Q1. Q3 is 0.75 of the data, and Q1 is 25% of the data. Well, 25% of the data is going to be falling in here, but not very far, because this went up to 0.21. So Q1 is going to be close to 20. And then to get myself up to 0.75, I need to add again. 0.53 plus 0.27 would be 0.80. So Q3 is going to be close to 40. Because I'm going to have to go almost all the way to that boundary to get up to 0.75. Well, what's the difference between 20 and 40? 20. That is the maximum possible IQR here. So when I look at these choices, 25 minutes, that's too big. So it has to be choice A. You could also sketch this out as a histogram, which I would highly recommend doing for a visual. I did not have time, though, because the bell's ringing in like less than a minute. But you could sketch out a histogram with the frequency on the y-axis and these different boundary lines for the buckets on the x-axis. I will see you guys tomorrow for your exam. Good luck with everything tomorrow morning.